Good morning, everybody. I'd like to welcome you to our latest webinar in a series that we've been running this year called Integrating Heat Pumps in Process Systems. Format for today is a technical talk followed by a question and answer session. We have a panel of learned people on to discuss this with us. We'll progress through a series of housekeeping slides. So just so everybody knows, this event will be recorded and it will be made available on our Process Industries YouTube playlist. All attendee media are disabled to allow for a smoother presentation, but you will be able to pose questions in the chat. So I look forward to some good questions at the end. Registered delegates will receive a CPD certificate, provided they attend for the full duration. Questions can be submitted through Q&A or the chat tabs available at the top right of the screen, and we'll answer as many as possible within our limited time. And slides will be made available after the meeting. To ensure privacy and data security, AI chatbots are not permitted to create notes or transcripts. Just a bit of background. The Process Industries division serve as a central point for mechanical engineers to connect, share expertise, and promote best practices within the process industries. So we have a large number of previous webinars, and we're always open to suggestions for new material. So feel free to join our meetings or work groups if you feel like doing so. Quick note about equity, diversity, and inclusion. Importantly, we believe engineering is for everyone. Our vision is to foster an inclusive culture where all members, employees, and the wider engineering community feel valued and develop a sense of belonging and are empowered to thrive. We're committed to embedding inclusion into every aspect of our institution with support from the People and Culture team, our Culture and Inclusion Committee, and our Culture Ambassador Network. We celebrate diversity amongst our members, employees, and the wider engineering community to ensure we meet the needs of our global community, driving progress and innovation in engineering for the benefit of all. So without further ado, I'd like to introduce our speakers for today. We've got Abhishek Bhatia, Chair of IMechE Scottish region and Managing Director of Integro Design Engineering Associates. We've got Stuart Scott, who's Professor of Energy and Thermodynamics at the University of Cambridge. We have Yasser Mahmoud Larini, who is Professor of Thermal Energy Engineering at the University of Manchester. We've got Bob Hayes, retired, but a member of the Pharmaceutical Technical Advisory for the IMechE. Daniel Wells, who's the National Consultant Specialist for UK and Ireland from Spirax Sarco. And Inigo Matas, Technical Director from IDEA and Distill RE. So quite a broad spectrum of academic and industry specialists. So I think without further ado, I'd like to ask Abhishek to start the presentation.
Thank you. Okay, good afternoon, everyone. Inigo, if you can switch to the next slide. Firstly, thanks to the IMechE Process Division for inviting us for the second webinar on industrial heat pumps. Inigo, if you can, yeah, second slide. Just by way of introduction, I'm a chartered mechanical engineer with experience across the chemicals, energy, food, and drinks sectors, particularly in delivering and managing multidisciplinary projects. I'm the managing director at IDEA and Distillery, which provides support to process plants in their transition to sustainable operations involving energy recovery, transition, electrification of process heat using technologies like heat pumps. So much of what Inigo and I will share today is drawn from our project work with clients who are actively pushing for more sustainable operations and focusing on net zero strategies. Inigo, next slide, please. Just to recap, in the last webinar, we covered some of the key concepts around industrial heat pumps. We started by framing the challenge, which is around the global energy use and emissions from the industry, and the need to decarbonize heat through electrification as one of the strategies. And that's where heat pumps can play a very important role. We explored energy management strategy like reducing, reusing, and recycling energy, which positions heat pumps as a practical way to reuse and recycle waste heat and electrify thermal demand. Then we covered some of the factors like temperature lift, heat sources, and sinks, coefficient of performance, COP, and the factors that affect performance. We also looked at different heat pump technologies like mechanical vapor compression, mechanical vapor recompression, and TVRs, along with discussing some of the refrigerants that are commonly used and how selection impact their heat pumps efficiency, safety, cost, and from regulations point of view. Finally, we acknowledge the real-world challenges associated with integrating heat pumps. This is where things get tricky when it comes to integrating heat pumps within the process plants. And that's exactly what we are going to focus on today. And how do we actually integrate heat pumps into process systems? And to take us through this, I'll hand over to our process engineering director at IDEA, Inigo Mates, who's been working closely on multiple live integration projects across various sectors. Again, don't worry if you missed the previous webinar, as a recording for it is on IMechE Process Division YouTube channel. Plus, Inigo will be covering some of those concepts again today to introduce some of the people who might not be very familiar with the concepts that I just recapped. Okay, over to you, Inigo. Thank you.
Good morning, everyone. First of all, I would like to thank the IMechE Process Division for inviting me to speak as part of this series on heat pumps. It's certainly a great honor. Like, so way of introduction, I'm a chartered chemical engineer and MBA, over 25 of experience in energy-intensive industries, including petrochemicals, chemicals, lately on the spirit sector. I'm currently the process director at Integral Design Engineering Associates and Distillery. In much of my work focuses on the full project lifecycle. It goes from conceptual design and feed through the commissioning startup, specialists as well in process optimization to reduce waste energy and improve the overall site energy efficiency, including conducting energy audits and supporting the client in their decarbonization path. Before I start, I want to share a big secret. I will deny if Javi asked me again, but I must confess I wanted to be a mechanical engineer myself when I finished school. Circumstances pushed me forwards towards chemical engineering, which was closer to home, more affordable. But today you're getting a chemical engineer with a mechanical engineering heart, I would say. Before we dive into each of the sections, I would like to start to set up a bit of the context. So heat pumps in the process industries are often discussed as a single technology, but in reality, the success depends entirely on how well we understand the process itself, We need to identify the right heat sources and sinks, mapping temperature profiles, and understanding when heat is actually available. These are all crucial steps. A good integration is rarely a utility exercise like some people think, when we speak sometimes at the beginning of conversation about heat pumps. It starts with process knowledge and a clear understanding of how energy flows through a site. In the next few slides, we will explore how to identify opportunities, how to match the sources and the sinks effectively, and how tools like pinch analysis and key diagrams help reveal what is often hidden at first glance when we look at the site. We will then finish with a section which is a bit of a deeper review on some of the available heat pump technologies and how to implement them, like effective cases of implementation in the real world. Okay, so those two main parts. The first one deals with is how to, and we will continue follow with the applications. So the first thing we have to do is to identify heat sources. They come in many forms. Some can be obvious, like an effluent stream, a condenser where we are removing that energy. I would say, like, as a key, we normally tend to look at cooling towers, like, that is a way of releasing the energy from the processes into the environment. So following those systems is a very good way of finding where are the heat sources. Many times people refer to this as traditionally waste energy, and nowadays we say, like, waste energy is not really waste. No, it can always be used. So, and which is the great advantage of the heat pumps. They allow us to recover and recycle this energy rather than let it go unused. Of all those heat sources, we could classify them in two categories, because many people think of heat pumps as maybe they have something at home, or that kind of heat pump is one where the heat source is continuously available. We have here on the left, that could be the effluent. We could have an air source heat pump, which is taking energy from the air, or it can be a river or a body of water, like underground water. The second category is these ones on the right, where we have what I call process-dependent heat sources. And in that category, we can find dryers, the chillers, the coolers, air compressors, a condenser, everything that I have shown there. These are integrated with the process, and their heat availability depends on the operating phase. Normally, these are more rewarding. They are at higher temperatures and offer higher potential. However, we need to understand clearly how they operate, because they're not available all the time. Yeah. Okay, so when we talk of those two types and categorizing the continuously available and process-dependent heat sources, the first one, because we are using energy that is contained in the air, in the water, they can start a process. By that I mean, like, they can supply energy in the same way that the boiler does. They can produce a steam. On the other hand, where we have the process-dependent heat sources, which are integrated with the process, as we were saying, we cannot use those heat pumps to start. And this is something that sometimes clients are surprised. The first thing, we still need the boiler to supply, let's say, a steam to a distillation column. We need to establish the distillation, and only when the distillation is active and we are recovering heat from the condenser is when we can switch into the heat pump. So we will be stopping the fresh steam coming off the boiler and then running off the heat pump. But so implementing a heat pump doesn't mean necessarily that we can get rid of the boiler. In this case, we will still need the boiler, we will need the cooling tower, or whatever, the way we are removing energy of the system. Now let's look at the heat sinks. Again, some of them are probably the same places where we took the energy from, so we can have a system where we can produce hot water. We can put the heat in the form of a steam. We have a steam production into a heater. We can power dryers, evaporators. We can even use this as a space heating. It's an easy way of recovering that waste energy, but sometimes it's at a smaller temperature. And with the steam, we can go back to a distillation column, where we have extracted the heat at the top. The critical step is matching those heat sources and the heat sinks. So how do we do this? So there's a lot of different approaches, opportunities. The best way is to follow the waste heat energy management hierarchy that we can see here in the screen. So we need to go in order from top to bottom. So the first thing we try to do is to prevent, no? Like if we can modify the process so we don't have to use energy or as much energy. Sometimes that can be a bit complicated, but it will be the first one. Then we move into reduce or reuse, which are similar, is basically reusing the energy within the own system. Yeah, and that, for example, a very good tool in doing that part will be the pinch analysis. Once we have exhausted and reviewed all those parts is when we will move to heat pumps, no, and recycle energy. Some people want to jump into that at the very start, but the cost of heat pumps can be significant. So everything we can do to reduce, normally they will come at lower price, lower capex, because it's through the heat integration, heat recovery. Yeah. So sometimes we also see that there is no delta T. That's the moment where we will move into the recycle part and the heat pumps. Okay, so talking about what I was just mentioned, the pinch analysis. As you know, pinch analysis is a systematic method for identifying the minimum energy requirements of a process. We examine the heating and the cooling heat flows, and that allows us to determine the point where heat recovery is maximized. Here on the screen we can see, for example, a trend, like that red line. That will be, we have the composite curves, we have the hot, that is a sum of all the streams that require to be cool, and the blue line corresponds to the cold composite curve, and that is all the streams that require heating. For example, in this case, the total heating required is 2,704 kilowatts, but we can overlap both lines, both curves, and we will have an integration of 2,127, which leaves us with only requiring heating for 577. So it's a very good method because it allows to establish the optimum, what is the minimum heating and cooling that the system requires, and it's good to set opportunities and to establish how to implement them. Okay, so this will be more on the reduce part. Today we're focusing more on the heat pumps. Sorry, I just wanted to touch one moment on this part. I think traditionally when we have spoken of energy, we have always looked at energy like steam coming off the boiler, maybe look too much in the detail of the energy, of the temperature of that energy, which is a very important thing. The level of exergy of a steam at 200 is much higher, can produce much more work than a steam at 120. In the past, we used, without maybe looking with too much care at what was the temperature available. So something that the pinch can give us as well. This is from the composite curve. We can produce what is called the ground composite curve that we can see here. This part in the center will be like the pinch point. Above is part of the system that requires energy supply, and below is where there is like an excess that we have to remove the energy. As we can see here, like one could say, like, look, this is all the heat that needs to be added, and we can do it with a steam at 200 degrees. That will be quite easy, but that prevents from using energy at lower levels. For example, most of that could be done at 140 degrees. This part could be done at 180. So why is this so relevant on the heat pumps? Because as we will see after, the COP, as Avi mentioned on the previous webinar as well, is very related with the lift. So we will always try to avoid lifting too much energy because that's going to result in a smaller COP. So again, the pinch is very good at helping us to identify what are the actual temperatures required for each of the energy packages. Okay. What are the support tools that we have when trying to implement a heat pump? A very known one is the Sankey diagrams. They help us understanding the magnitude of the energy flows on a site. They show where the energy enters, where is consumed, where is lost. These diagrams offer reveal like surprising imbalances. Or I think making people aware of how a site is running is very helpful, because sometimes we just miss, and when we look at the Sankey, sometimes we say, wow, I didn't know that was as much energy. So I think it's good for everyone just doing that, understanding how energy is used, which is a very important thing in nowadays. Always, but especially nowadays. The other tool, we call them the energy flow diagrams. These will be more, they go a step further, yeah, so they map with the temperature levels and with the flow, the flow of heat through the process. We show here the steam, we show the cooling. If there is like here, like for example, this process is like exporting energy into this other part of distillation, They can be complex at the beginning, normally that they're different levels, but they really help to simplify complex processes and make it easier to identify the points, where a heat pump can provide meaningful value. That is very important. Okay, so what does a heat pump do? When I was at the school, I was told that you cannot define a word by using the same word. However, when the people ask me, I would say like the most accurate way that I can think of to describe what a heat pump does is to say that simply a heat pump pumps heat. Maybe it sounds very obvious, but I don't know why, at least in my head, I never look at them in that way. So in the same way that a centrifugal pump, for example, can pump liquid uphill by applying work, we can do the same. We can increase the temperature of the energy by applying work. As we can see here in the screen, we can start with the steam. That the steam is going to be used to produce distillation vapors, and finally we remove the energy in the form of cooling water. By doing this, the temperature is going down, as per the thermodynamic principles, the entropy increases, the temperature is going to be flowing down. So energy is conserved, but the exergy not. So can we move this package of energy back? Yes, we can. We can do that, but again, to conserve energy, we must use work. Okay, so that's what we were saying. It's possible, but the higher the lift, the more energy we're going to have to use. If we follow with the analogy with the centrifugal pump, if we want to pump liquid from here 2 meters high, or if we want to do it like 1 kilometer high, the amount of energy is going to be a lot higher. So here we need to be very careful, and this is what I was talking about, the pinch analysis. Like every temperature needs to be ideally provided at the minimum temperature that we can do. In the same way that when we are cooling, we are not going to be using like chilled water. We can do it with cool water, or we can even recover energy into a process. I think when the heat pumps a few years ago, and people will be saying, this heat pump can do this part, or very good, have this performance, the other one. I really like this trend, like this is prepared by the European Association of Heat Pump Manufacturers, and we can see which are the COP values associated with lift that we can read here on the x-axis. As we can see, the higher, as the lift decreases, the COP is higher. In the same way as the temperature lift that we are asking the pump to produce increases, the COP decreases quite a lot. So this is a very important point. COP, we all know, but just as a reminder, so we define COP as how much heat output can we get in kilowatts, for example, a unit of energy, divided by the electrical input. So this will be this ratio of energy that we can achieve. Okay. Just one thing on the COP, just to give a bit more information. Like sometimes I was speaking with a client one day. That COP is 10. The savings are not always proportional. For example, in this table we can see that when the COP goes from 3 to 4, the savings go from a 66 reduction to a 75. So that is almost 8.3. However, when we are going from 11 to 12, that difference is a lot smaller. So in this case, we will be speaking of only 0.8%. So there is a big difference. We can see in the trend at the beginning is like more linear, like if the COP is 3 compared with an electric boiler that has 1, the savings will be accordingly. But when we are going from a COP of 10 to a COP of 11, or in this range, as we can see, that the savings are not as big. Okay, very related with this part. Sorry, I thought I had a slide here. Sorry. Is the spark gap? When we I will show it in the same way. It doesn't matter. Okay, so when implementing the heat pumps, there are several challenges that we need to consider. Yeah, on one hand, we have like maybe there is an impact on the product quality. We don't want to disturb the process. If a condensing temperature is 30 for whatever reason, we cannot maybe make it 100 degrees or 90 because that will affect the product. We have as well, if we want to implement a heat pump, what about the downtime required to implement it? What about the electrical requirements? Sometimes there can be like a high consumption of energy, space availability. And we have as well the cost efficiency. We have the CapEx, no, the money required to implement the pump, and also the OpEx. So in the OpEx, because most of the time the electricity is going to be the driver for the heat pumps, the price of electricity plays a big part, and this is particularly a big challenge in the UK, and this is what I wanted to show this. So this is the spark gap. So these represent the ratio between the cost of amount of unit of energy in if it was electricity or if it was gas. As we can see in the UK is the highest, among the highest in Europe. It's here 4.5, it changes, but it's quite a high number. So what does this mean in practice? Like if we were comparing a system that runs by gas with one that is running with electricity, we need the COP at least to be 4.5, because at that point it will be equivalent at the cost we will have if it was a gas. It's a bit less because we have the efficiency of the gas boilers, which is not 100%, but it really explains why in some countries like heat pumps are more widely implemented, because the cost, the European average is 2.7, but some of the Nordic countries have even smaller values. I've said the other point that comes out of this is what I was saying before. It's very important that we look at how to reduce the energy consumption. So it's not just jumping directly into the heat pump. We want to try to use the other methods to reduce energy consumption or to make the most of it, because the heat pump can be a bit more expensive. That is also going to help reduce and make a heat pump project more attractive. Okay, designing for success. On the previous webinar, it was talked like how important it is to understand the process, not especially when we are talking about these heat pumps, when we are implementing, no? Like having this good process inside highlights opportunities like the effluent, using the river, using air, like all these are quite clear, no? But what we can get of the process, and I would say this efficient way of using the energy within a process, is a bit more complicated, and that's where we can use what we were explaining before, no? Understand the thermodynamics, make those mass energy balances, understand very well the utility interaction go very deep in the process basically. As a reminder, like integrated heat pumps, they work with the process, not alongside, as we can say of the boilers, no? And that will be the same case for the standalone heat pump that I was referring to, operate with air, water, that they can operate completely independent and they don't need the integration. Everyone has got like a good part and a bad part. More challenging integrating, but the potential is higher because the temperatures are higher in those streams. Yeah. Types of industrial heat pumps, we went through on the last webinar through this part, no, open cycle, closed cycle, and the different parts. So in the second part, what we'll be looking is at examples of how to implement those, or implementation of those heat pumps. Yeah, we will start with the mechanical vapor compression heat pumps. No, how does it work has been explained. No, basically we have a heat source, and by compressing these low pressure vapors to higher pressure and the temperature, and then we're going to be releasing that heat through the condensation of that vapor into the heat sink. Yeah. Okay, so an example of how to achieve that is what we can see on the screen. Here we have a double stage ammonia heat pump. On the left we can see like this will be the heat source, and this is I would say easy to implement. It's just going directly into the cooling water return loop. Yeah, and it's water in this case at 30 degrees, which we are going to be cooling and producing or recovering heat at that interval of 30 to 20. So this, on top of the heat source that I'm speaking a lot of, that save energy, it's also saving, we don't have to cool the water in the cooling tower, so that's going to reduce water use, if it's a cooling tower or if it's another one. In any case, it will be another source of energy reduction as well. Why does this system has, well, on the heatsink, we can see that this is boiler feed water that was coming at 10 degrees and is reaching 85. Because the difference in temperature between the 30s and the 85 is quite high, it wouldn't be possible to have just a single stage, a heat pump. That's why in this case, we have 2 stages of compression. So this is going to provide the energy to evaporate the liquid. Those vapors are going to be compressed. We have a second separator, and those vapors at higher pressure / temperature will go into the second stage of compression. Those vapors will go into this condenser, which is giving that energy. And there is even a subcooler, which is increasing further the COP of that heat pump and doing the first preheating of the cold water going into the system. So this is a very, I would say, standard application and well implemented. Another application could be when we use a mechanical vapor compression, but in this case it's not just a single type. There are 2 in cascade. It's combining what we can see at the bottom, which will be a air source heat pump, and we have another level which is a water source heat pump. So what we are doing here is we are using the air outside. Again, if this is in summer, the COP will be higher because we are abstracting the energy at higher temperature. If it's winter, it won't be as high. We need to design for the winter case, which is the one with the lowest COP. So this lower temperature heat is collected into the air source heat pump and is producing this first level of water, which is at 35 degrees. And we have these integration tanks. The good thing about having these integration tanks is like when you are designing this, as we know, like sometimes there are benefits in the electrical tariff during nighttime. So it allows maybe to run your process during night, accumulate that water, and maybe that can be used during the day in the other part of the process. In the upper part, that 35 water is the source of energy for a water source heat pump that is coming back. So it's cooling from 35, 30 degrees, and it's going to allow us to produce this water, which is between the 75, which can be used in the users, and is returning at 69. Same as the thing I was saying before, traditionally space heating systems that were running at higher temperature, that from a heat pump point of view, that's not ideal. It's reducing the COP. So we will try to make these temperatures as low as possible. That maybe is in the way of changing the radiators to increase the area, not to achieve the same heat transfer. But it's also a very good application, this cascade system using both. Again, the idea of using both 2 systems is to maximize the COP and the performance of these systems. So what are the key points around the MVC? So they can work with liquid sources at low rate, also air, but normally this is more around like smaller temperatures. We can have temperature leave 20 to 100 degrees are feasible depending on the compressor selection. It's good for allowing to integrate multiple processes. If we have that hot water buffer, we can maybe have some recovery at lower temperature. We can also recover heat at higher temperature. So this gives like a very good operational flexibility. Going back to refrigerants, natural, synthetic, different parts. I'm not going to touch a lot of detail in that part. Normally, I've been saying that heat pumps normally run on electrical power, but there are also options to, some of them can be gas driven, which can be used if, for example, there is a place where there is no sufficient power or there is no good a network of arriving grid constraints basically that we can find. Applications, so as I was saying, most of the time hot water loops that can supply heat for preheating or heating duties. Normally this is below the steam temperatures. That's why preheating, what I would call preheating or heating at these first levels. They're good for recovering heat of cooling water loops, warm effluents. I would say like temperatures below 50, 60 degrees is a very good field for them. They provide this combined heating and cooling. So it's not only not giving us the heating, we don't need to use anymore the cooling tower or a fin fan, whatever we're using to remove the heat. Sometimes they can act as well as a standalone heating systems, where no process integration is required when we're using the air or a body of water. and it helps not to this electrify the heat demand in a site. Yeah. Okay. The next one we move is a TVR. So TVR will be is a very different system. We say thermal vapor recompression. For example, this is quite used widely in the spirit sector. So what we are doing in this case, we have some vapors arriving to a condenser. In the past, traditionally this will be removed by using cooling water. What we're doing in this case, this is a falling film evaporator. We supply condensate, which when going down is going to produce vapors, vapors because we are slightly in the vacuum. So we have these vapors. These vapors, the temperature is below the temperature we need. This is boiling at 100, let's say this is like 106 degrees. So what we are doing is we are mixing those low pressure / temperature vapors with motive steam coming off the boiler. So by mixing both, we can recover all the heat that we have that was coming from the condensation of the vapors and is going back in the process. So the two main elements will be this falling film evaporator and the ejector, what we are mixing those two streams. So something we need to realize when we are looking at the TVR is like, if this is the system, no? As we know, there cannot be accumulation because we need a continuous supply of steam, which is the energy supply into the system. This will accumulate. So we also need to remove energy. Yeah. So how do we do that? One way, for example, is to create hot water. We also removing subheat if, for example, the product needs to be subcooled. So we are recycling, let's say, one part, 50, 60%, but another part needs to be removed. The ratio of motive steam required will depend on the temperature of these low pressure vapors. The closer that we are to what we need, the smaller the amount of high pressure vapor that is required. So the key points, so in this case, the heat source is the process. Now we are capturing the heat of condensation of those vapors. We can only achieve a moderate temperature lift because of the way we are doing the process. Normally in this case we will integrate the heat within the same, not like in this case we were extracting the heat from the condenser and it was putting it back into the reboiler. There are more effective technologies, but the good thing is that the capex is really smaller and they don't need a significant amount of electric power just to move a bit on the condensate and not as the heat pump that we were speaking of before. And in these cases, we use a falling film evaporator to maintain to be able to capture. It's the most effective way of capturing energy, producing low pressure vapors in a condenser. Okay, applications. So widely used in evaporators, in the food, chemicals, wastewater treatment. Also, like everywhere where we have a flow of vapors, is a potential candidate for a TVR system, and it provides as well a simple and low maintenance way of reducing the steam consumption. Okay, then we go to the next one. I will call this like an evolution of the TVR. Yes, so this is the MVR, which is a mechanical vapor recompression. So in this diagram provides the basic concept of how it was. No. I really like this technology. People that know me, I always speak very well of these. So basically what we have here is we will have the process, we have the dilute feed coming to the process, we will have this heat exchanger which we are traditionally providing steam, and we will be evaporating water. So this is a falling film evaporator. What we are doing is these low pressure vapors that we are producing, we are going to compress them, but we are not going to use an ejector to mix them with higher pressure steam. Instead of that, we're going to be using this fan, which is going to compress that vapor to the point that that vapor can be used in the system. So really what we are producing is going back directly into the system. As I was saying before, we need to add a bit of energy and a bit of work, not to increase the temperature of the energy. If this was, for example, a system that was distilling like a simple single component liquid like water, for example, that we wanted to produce, the efficiency is extremely high. Why? Because the temperature difference is very small. Look, on a normal distillation column, the temperature at the top are smaller, but if the temperature in this case is the same, we just need to increase a bit of delta T, maybe 5 degrees above the condensing temperature to drive the process. So here the COPs can be very, even above high, can be really, really high. Yeah, and this is a very good system. So another application, not for just a single component, where we have like a multi-component distillation. Here on the left, we can see like a conventional distillation configuration, where the live steam is provided at the reboiler, and the heat is removed in the condenser using cooling water. Traditionally, we always used to say, like when I was in uni, like, distillation is a great methodology, but it's very expensive. I would say that is something of the past. It's no longer the case. So how do we will make it in the more modern configuration? In the top, instead of having that condenser, we will have just a condenser, not still this falling film evaporator, and we will be creating those low pressure vapors. I have left this maybe for a subcooling or when this is not running at the beginning, so producing the reflux, the top product. Those vapors, they can be compressed using these fans. How many stages of compression do we need? But it's really going to depend on what is the delta T between the base temperature and the top temperature. No? So the closer, the smaller the difference, the less stages of compression. Traditionally, we will say as a rule of thumb that each stage of compression can provide like 10 degrees of lift. So in this case, like 30 degrees. Again, looking at each system will allow us, but it's a very, I feel like more and more we are seeing implementation of this in distillation columns because the savings are very, very significant. Okay, so what are the key points? Again, similar to the TVR, the heat source is the condensing vapor, normally from the same process. The vapor temperature, normally at the beginning this was more using the continuous operating. The vapor temperature was constant and this was operating at the same point. But this is easy to control. The leaf is just, by fitting a variable speed drive on the fans, we can adjust what leaf is required. So even on batch systems, we also seen more recently like implementation of this type of technology. The typical leaf, 10 per fan, what's going to happen is, theoretically we could go 70, 80, but the cost of each of the fans is important. So, when you're going up, beyond 3 or 4 or 5, it becomes more difficult from a CapEx point of view. But again, knowing the spark gap, knowing the exact conditions for each system is important. In these systems, I didn't say that for the TVR, but we are not using a refrigerant. No, we are using the same fluid as to transmit the energy. Normally electrical power for this kind of compressor, which these use a significant amount of energy. It's very good technology for evaporation, concentration duties, where we have a stable vapor generation. Applications, evaporation, flash vessels, for example, where we have a stream that in the past it was low pressure, so now we can increase the pressure, temperature of that stream and use it. When we are trying to decarbonize a certain process through using electrification, we can then have like hot water loops as well, where the vapor cannot be reused. We could do that, but again, saying what we were saying before, we want to use the energy at the highest temperature possible when we are producing that part, as well giving us the heating and the cooling part. Yeah. Okay. Another one which is a combination of the ones that I have explained so far. So what we can see here is that there are cases where maybe we will be doing like hot water, but in many processes we need the steam, industrial applications. So the MVC mechanical vapor compression pump is going to be very good for giving us maybe that 80 degrees, but when we go to the vapor, to the steam temperatures, it's not as efficient. So in those cases we can cascade. So this example that I'm showing here on the screen, this will be a dryer, and we will have these vapors, air vapors, it's a humid air, so it's giving good energy, so we can capture that in this loop, which can be like a water loop, and then this will be the heat source for a ammonia heat pump, another type of refrigerant, as we were explaining before. It's going to give us that water at 85, 90 degrees. The concept is the same as we had in the TBR or MBR. We will be flushing those, we will be flushing condensate at reduced pressure, and after we will be feeding those vapors through an MBR, number of stages depending on the temperature required, and that goes back to the process. So we're closing the loop here in this process, no? So capturing the heat, that waste heat recovery going into the MVC heat pump and then transferring to the MBR. Yeah, so this is what we would call like a hybrid system. Yeah. Okay, so again, what is the advantage? No, I think they have really helped in the steam production with very good efficiency. So we can go from 30 degrees, as low as 30 degrees into steam production. The COP is quite good, I would say, for that range. For something that is like 105 degrees temperature on the steam, the COP will be around 3. If the heat is available not at 30 but even at 40 degrees, it will be higher COP of 4. It allows us to produce a steam in stages where the MVC heat pump is not as good. We can integrate as well like multiple processes, and we can produce the steam. We can also have the first part making hot water in another part of the plant. So it's a great way of creating like a heat recovery network, capturing and also producing heat at different temperatures. Okay, applications. For example, sites that need the steam but have large amount of low-rate heat. No, that has been a constant in my career as professional. Sometimes we will have a lot of hot water, but we didn't know what to do with that hot water, which is the point that we have to use all of it. These will allow us to produce the steam. Also, like places where maybe we need to keep what I was saying before, the condensing temperature at lower values. We cannot really be going higher for recovering the energy because that will affect the quality of the product. A good one that I really like as well is like sometimes implementing a heat pump can be complicated because there is not a lot of space. Here we just need to make a tie-in on the cooling loop, take it somewhere else where we can implement the heat pump. Yeah. Okay, so we have gone through all the different parts. So as a summary, I would say like we have seen how a heat pump, like the one that we can see, this beautiful machine that we can see here on the screen, can be integrated into an industrial process. No, so heat pumps are a strong option for decarbonization and increasing the process efficiency when the right heat source and the heat sink are available. The key point is to understand the process in detail, as we have said a few times. Without accurate temperatures, duties, load profiles, and knowing of the operational constraints, it's impossible to design a system that makes the most of it and is reliable. It's also essential to begin, as we were saying, by reducing the energy consumption, which is going to help us to decrease the capex for these implementations. Energy efficiency must always come first. Yeah, lowering the demand, improve the thermodynamic profile of the site, can help us to reduce the size. Yeah. Heat recovery is valuable, yeah, but we should always avoid that unnecessary consumption. And sometimes we forget this, trying to move just into the solution. When the heat pumps are applied correctly, they help us to reduce the steam demand, to cut the emissions, to improve the overall site energy consumption and economics as well. No? With the right level of processing side, they become a powerful and practical tool for electrification and long-term decarbonization. Thank you very much to everyone. Thank you.
The capex required between TVR and MVR can be quite significant. So just to kind of add that as well, that even though MVR are more efficient, compared to TVR, the price difference can be quite significant, and hence spark gap and other factors become quite important, depending on the applications.
Okay, thank you, Abdi and Inigo, for some very interesting presentation and explanation of some typical systems. I'd like to go through the comments and questions that have been raised in the chat. we had a comment saying that the graph regarding COP against temperature lift should be updated to account for new, more efficient technology. Maybe a quick comment on that one, Abdi?
Yeah, like, this is taken from a paper that is from 2023, and it could be even more, no? But the first part, I would say, like, we're never going to reach the ideal performance, no? But we are getting closer. So every time, yes, we are seeing that those COP values are getting better for a certain lift. Yeah.
Yes, I think I think we have to bear in mind that we're giving an overview in these slides, and it's probably illustrative of the speed at which the technology is improving. The next one was, do you have simultaneous heating and cooling options to save space and recover energy?
Yeah.
Yeah, I think even though IMechE didn't show that as a configuration as one of the process application, but I think before the slide was presented where you mentioned combined heating and cooling recovery, where in some applications it goes hand in hand, it all then goes back to the heat sources and heat sinks available and how you match them. So even though IMechE didn't present the configuration through the diagram, I think it was mentioned in one of your slides, IMechE, simultaneous heating and cooling as a potential.
Yeah, I would say, for example, a very typical application is those processes where there is a part, the stream needs to be like first heated and then cool, yeah? So the heat pumps can do that two parts simultaneously. So they can do a bit of reducing, but also transferring the energy in a very efficient manner. So yes, it's quite implemented, yeah.
Okay, thank you. Then we had a discussion about the cost or the cost of a system for smaller scale systems, to which Daniel responded, and there was then another comment from Ollie asking if MVRs are the tool of choice in many cases. I think fundamentally it's about the basis of this is about looking at your processes in particular and the detail of your processes, and then working out an integrated solution. So it's not a case of one size fits all. It's about designing a system for your particular process. So I don't know whether any other members of the panel would like to come in on that.
Yeah, I think Richard, that's a good point. The sizes for the MVRs have evolved over the last few years, where even for batch distillation process, where there's more cyclic demand as well as smaller applications, there are now technologies available which weren't previously available, and MVRs were usually seen as kind of more adaptable for large kind of continuous process type applications. So there has been evolution. Again, we wouldn't want to name any suppliers here on this forum, but there are range of, again, it's all driven by the process. If you can first see what your process involves, what it requires, and give all that information to either the consultants or the suppliers, they should be able to match that to tell you whether it's MVR or any other type of heat pump is the right fit for your application or not.
Okay. Then we had a question, is HVR's hybrid system suitable in Hong Kong? I think we've probably answered that in the sense that you have to look at these systems within their particular environment and just decide what is actually best in your situation. Regarding operation during startup, is it best practice to include a backup hot gas generator into the designs? How is the lack of source heat handled during startup?
I think, as IMechE mentioned, that generally because it's a process dependent heat source, You generally need to have either a boiler or some sort of a heat generation or energy generation device, yes, at the start to get the process up and running.
Yeah, exactly. They wouldn't be able to start from zero. Like you need to establish that boiling, no, that distillation, that condensation. At that point is when you let to transition into the heat pump. Yeah.
Okay. And then any examples where more remote industry has managed to work in cooperation on joint projects to sell on recovered energy hot water to other industry or residential projects?
Oh,
It's another one of those questions that's looking at the system within its actual environment, isn't it? If you've got spare heat, then obviously you can sell it, but you have to has to be
yeah.
integrated with your neighbors.
I think each industry brings unique challenges, opportunities, along with the wider constraints that Inigo mentioned, and that could be availability of certain type of utilities, prices, electrical infrastructure. So again, without being too overly specific about any given application, again, would go back to say, I think one of the things we had previously mentioned was that when it comes to applying this energy management hierarchy, where you look at reusing, recycling heat, the point that goes in tandem is that if you do still require heat generation, and for that, whether you need fuel, electricity, gas, oil, and you're further trying to decarbonize your overall process, it all depends on what utilities are available in the region, whether it's Hong Kong, whether it's any other remote location. All these constraints kind of play a key role in designing the whole system, and that's why kind of starting with what can be done within the process and then going further upstream to say what else can be decarbonized in order to bring the emissions down, but also be pragmatic about the operating cost of the system.
Okay, thank you. And then just briefly, we'll have to take one more question. What are the biggest technical or organizational barriers to integrating heat pumps into existing industrial processes, and how can companies overcome them?
Okay. Well, I would say like those barriers. I would say like maybe they fall like in two main groups, like temperature, integration, complexity, and organizational readiness as well. Like technically, that the main difficulty is achieving that the required supply temperatures efficiently. Like many processes still need heat above 100 to 120 to 150 degrees. That's what the heat pumps are less competitive. Yeah, although heat integration can maybe reduce the temperature leaf. So that is technical will be the first one. The second one is that system integration. No, like some industrial sites they have fragmented heat sources and sinks, variable loads and legacy steam systems. The heat pump is not a plug and play boiler replacement. Yeah, so successful integration, as we were saying, requires the data, the stable conditions, close coordination across the engineering disciplines. And
Yeah.
finally, I would say is organizationally, the heat pump projects are often framed. People think of this like a replacement swap, and this is a bit deeper, no, because they require the system optimization that cut across different departments in operation, utilities, they require like this shared ownership, with some organizations still there. I think there needs to be this change in the approach of how do we manage energy overall.
Yeah.
Okay,
And
thank
also,
you.
sorry, Richard, just on the spark gap graph that Inigo presented as well, which talks about the key barrier to electrification, which is where the heat pumps kind of falls, is the electricity prices. Where in the UK, the difference between the gas and the electrical prices. So one of the things that government can try and policies can be driven to bring that spark ratio to make that lower, and it requires a long-term strategy, which then hopefully makes the adaptability of heat pumps much more practical.
Okay. Okay, well, I think time's up. So thank you. I'd like just to thank all the presenters for a very informative session. And I think we had some interesting questions too. I think for me, there's a lot of what we've got there is quite a lot of topics for future discussion. So we can, we've gone over it in quite a generalized point. So, downstream, I'm sure we'll pick up on some of these. I'd just like to, if I can share my screen. I'd just like to wrap up with a final slide. So just just finally, I'd just like to draw your attention to the process industries webinar recordings, which are available on the IMechE website, and there's a useful, obviously a useful QR code there, which will take you straight to it. So in due course, this presentation will be put onto that site. So you might wish to review some of the points that were made, particularly in relation to some of the questions which I think we possibly have answered during the presentation. So I think on that note, it's time to wrap this up. So I'd thank all the people who've attended, and again thank the presenters, and just a quick word of thanks to the organisers who've volunteers who've put a lot of effort into preparing these webinars. So from my perspective, thank you very much. And that's at this point, I'll say goodbye.
Thank you.
Thank you.